So hello everyone, welcome to our video on Mohr circle method for planar body. So in this video we are going to cover about why is Mohr circle an important topic, then derivation of Mohr circle followed by steps to draw Mohr circle, and also we will cover about Mohr circle properties and Mohr circle for the different cases like uniaxial, biaxial stresses or pure shear, how the Mohr stress is going to look for all those different cases. Finally, we will also discuss about the application of Mohr circle in other areas. Like in this video, we are mainly going to discuss about Mohr circle for plane stress phenomena, but the Mohr circle is applicable in different areas. Those things we will discuss at the end of this video. So let's start. So the first thing is that why is Mohr circle such an important topic? So first of all, the process of changing stress from one set of coordinate to another set of coordinate is known as stress transformation, and that can be done using the algebraic equations. Like suppose if we want to compute a normal stress at any plane that is inclined at a theta angle, we can directly write down the formula for sigma n and tau t. Sigma n corresponds to the stress that is normal to the plane, cutting plane, and tau t represents the shear stress that is present at that cutting plane. There are different ways also like to find those stress at any set of coordinates that is rotated by some angle theta using some transformation matrix or by any other transformation equations. But for this case, like I'm just going to write those equations. So if you look at these equations, maybe these equations look familiar with you if you are already into the strength of material. So these equations are simply representation of normal and the tangential stress at any plane that is cutting the component at theta angle with respect to the x-axis. Like I will give you the graphical representation for this. Like suppose if we have some element like this in xy plane, and if we are cutting this element by some plane which is making an angle theta with respect to the x-axis, this formula can be derived, and this formula will give the normal stress that is acting at this plane and the tangential stress that will be acting at this plane. Now this formula is sometimes hard to memorize because it also like contains the sign conventions that we need to remember. So what happened is that a person named Otto Christian Mohr come up with the graphical representation of this equation so that it will be easy to memorize. So he gave the representation for this sigma and tau t in a graphical format, and when he derived those things and represented those things using some graph table, he found that these equations can be represented as a circle. So that's why this whole thing is known as representation of this transformation equation is known as Mohr circle, because it gives you a circle and which mainly gives you, like at every point on the Mohr circle, gives the stress values that will be acting in sigma n and tau t corresponding to that plane for any value of theta at any point that is located inside the material. So this gives the whole picture that is currently happening inside your material. Okay, so let's start and first discuss how we can derive the Mohr circle. So to derive the Mohr circle, first thing is that we can go back to the same wedge element. So if you look at the wedge element, there are different stresses that will be acting on this wedge. Okay, now you can derive the formula for sigma and tau t by balancing the forces. Like if you balance the forces in the x direction, so there will be, to keep this wedge in equilibrium, there must be some force px that will be in this direction, similarly py in this direction, and then we can further resolve this px force as after converting it into like px. If we resolve it in this theta direction, it will give you a pn force, and similarly this tau t will also give you some other forces, the pt forces, and then we can divide it correspondingly by area to find the sigma and tau t. So I had already made a video on this. You can go through the link that I am going to put in the description to know how we can come up with the formula that I am going to write. So this is the formula for normal stress that will be acting in this direction, and tau t that will be acting in this direction. Now if we look at these two equations, what we can do is that we can write this equation in such a form that on right hand side only sinusoidal and cosine terms will be present. On left hand side it will be sigma and the constant term that will be present in these equations can be categorized. Okay, so let's write those. So we are going to get these equations. Now at this point, like suppose if uh, square this third equation and the fourth equation and then add them up, what we are going to get is that sigma n minus sigma x plus sigma y divided by 2 whole square plus tau t square, and on this side it will give, like for first term it will become sigma x minus sigma y by 2 cos square theta, and we are going to, when we are going to add it with the fourth after squaring it up, it will simply become sigma x minus sigma y by 2 whole square, because cos square theta plus sin square 2 theta will become 1. Similarly this term will also give you tau square xy, and because there is a plus minus sign and plus plus sign, so the other equations that if a plus b square 2ab term is going to cancel out from both the while adding 3 and 4. Okay, so plus 0. Now just by looking at these equations, do you are you able to recall like which type of graphical figure this equation is representing? So if you look closely, this form is exactly a equation of circle with sigma and tau t as horizontal and vertical axis. So that will be like, if you compare this thing, which x minus a square plus y square is equal to r square. So this is an equation of circle with center at a comma 0 and radius r. So what we can say is that we can get, just by transforming this thing sigma and tau t, these things can be represented as a circle with center sigma x plus sigma y by 2 and radius equal to sigma x minus sigma y by 2 square plus tau square xy. So here what we have done is that we have mathematically proved that what will be the center of this Mohr circle and the radius of the Mohr circle. Now let's see that without going into this mathematics, how we can plot just by using the graphical chart papers, how we can derive the get the Mohr circle. Okay, so let's first take a simple element that will be subjected to the planar stress system. So the stress system are sigma x, sigma y and tau xy. So the first thing that we have to do while creating the Mohr circle is to decide a horizontal and vertical axis. So for the Mohr circle, the horizontal axis is your sigma, that corresponds to the normal stress at any theta. Tau will be your shear stress, that will be the vertical axis. Okay, so it's going to look like this. Now the next thing is that we have to decide the sign conventions that we are going to use. So the sign conventions that we are going to use is that if the forces are tensile in nature, they will be lying on the positive horizontal axis. If they are compressive, they will lie on the negative part of the horizontal axis. Similarly, for shear stress, like if the stresses on the faces are producing anti-clockwise rotation in the element, they will lie on the negative shear stress axis, negative vertical axis, like in this region. And if those forces are producing clockwise rotation about the centroid of any element, they will lie in this part of the axis, like positive part of this vertical axis. So at this point, like if we want to represent this element and the forces that are acting or the stresses that are acting on this element in this chart of the Mohr circle, so let's do that. So if we first consider this face, so on this face, what we can do is that we can represent this x and y forces, that will be the normal and shear stress, as a point, because now the horizontal and the vertical axis are sigma and tau. So first thing is that if we look at the tensile stresses, what sigma x, what we can say is that it is tensile in nature. It means that it will lie in this region. Second thing is that if we look at the shear stress and the centroid, so what this force is doing is that it is producing a anti-clockwise rotation. It means that it will lie in the negative part of this vertical axis. So this X point is located somewhere. Now for this case, what we have done is that we have assumed that sigma y is smaller than sigma x. It can be any value, but for this case we are assuming magnitude of sigma y is smaller than magnitude of sigma x. Okay, we can give it this magnitude. Now here if we again look at this sigma y point, it is tensile in nature. It means it's going to lie in this part of this horizontal axis. And now the tau xy, this tau xy is creating a clockwise moment about this centroid. So this point will lie in somewhere in this first quadrant. Okay, so if we plot this line, plot this point, what we are going to get is that for these two orthogonal faces, we are going to get these 2 points x and y. Now third step for creating the Mohr circle is that we are going to join these two lines and find the midpoint of the line that is joining this x and y. So if we are going to join this line, here you can see that the midpoint automatically lies on the horizontal axis. So this will be the center of your Mohr circle, and the radius of the Mohr circle will be Cx is equal to Cy. Now here we are not going into much detail, but what we can do is that we can take the center of the circle and radius as Cx and Cy and draw a circle. So now this circle is known as Mohr circle. Now at this point, suppose if we want to derive the values of the center, like at what location of the horizontal axis it's going to lie, because for its center is simply equal to something a comma 0. So without using the formula, we are going to do that just by using the geometrical relationship. Now if we look at this point is sigma y, this point is sigma x. So the distance between these two lines, these 2 points will be sigma x minus sigma y. Now if we further divide, because these 2 points, if we are going to take a midsection of this line, what we are going to go is that the midpoint will be the C. So this side and this side will be equal for these cases. It means that this side will be from here to here. The value of this will be sigma x minus sigma y by 2. Now if we want to compute the location from this origin, then we have to add the value to this sigma y plus sigma x minus sigma y by 2. So this will be equal to sigma x plus sigma y by 2. Now if you compare with what we had discussed in our last slide, it is mathematically equal to the same value, sigma x plus sigma y by 2. So we had mathematically derived, but we can also graphically derive those things. Now if we want to also compute the radius, that what is going to radius, now here we already know this value, that is equal to sigma x minus sigma y by 2. Now this vertical axis will be your tau xy. Now simply if we are going to use the Pythagoras theorem, what we are going to get is that r is equal to square root of sigma x minus sigma y by 2 square plus tau square xy. So no mathematics will be required if we are directly playing with the Mohr circle. So if you are starting with the strength of material or mechanics of materials, it's a very good practice to start with the Mohr circle, because in those cases you don't have to remember any formula. You can directly using the Mohr circle derive any values, and we are going to look at those things in our upcoming slides. Okay, so don't worry about those things. So let's discuss about the second thing, like using the Mohr circle, how we can derive the principal and the maximum shear planes. So in this slide we are going to discuss about how we can find the values of the principal planes and the principal stresses. So suppose we have already created one Mohr circle by using the values of sigma x, sigma y and the tau xy. Now if you want to find the principal stresses, so what we can do is that we can recall the definition of the principal stress. So the definition of the principal stress was that any plane on which the shear stress is going to be 0 and the normal stresses are going to be maximum. So for this circle, there are only 2 points on which the shear stresses are 0. So these 2 points represent your principal stresses. So that will be sigma 1 and sigma 2. Now the angle that this corresponds with this horizontal axis will be your first principal stress, or that will be your second principal stress. So here maybe at first look you may get confused, like why we are measuring the angle with respect to this line. So reason is that, like, if we take a simple uniaxial case, okay, or miss a simple element, so the forces that will be acting at this face will be represented by this point x, and that's the reason we are measuring any angle with respect to 2 theta p1, and these are in the anti-clockwise direction. So what it means is that, suppose initially the normal is inclined in this of this face is inclined in this direction, so when we are measuring this plane, we have to measure in this anti-clockwise direction. So it means the plane corresponding to this 2 theta p1 will be something like this, and if we are cutting this thing, the plane will cut at this angle. Similarly, if we take this 90-degree, that will be something like this. Okay, so next thing is that how to find the value of normal stresses. So the normal stress, what it says is that, first, normal stresses are the planes on which the shear stresses are going to be maximum. So there are 2 points on which your shear stress are maximum. So these points directly lie above and bottom of the center of this Mohr circle. Because if we are going to take any other point, the value of the tau xy corresponding to this will always be smaller than the radius of this Mohr circle. So tau max is equal to radius of your Mohr circles. Okay. Similarly, if we have to find the plane corresponding to this maximum shear plane, we can again measure these planes. Like now in this case, what we are doing is that, if suppose initially the plane n cap, the normal of this plane is oriented in this direction, so in this case we are measuring in clockwise direction, so it means the plane will be inclined at this angle. Another thing to notice from the Mohr circle in this case is that the maximum shear planes and the principal stress planes are making a 90-degree. It means that in Mohr circle we always talk in terms of the 2 theta, not in terms of the theta. So in actual, this Mohr circle, though the difference between maximum shear plane and the principal strain will be 2 theta is equal to 90-degree and theta will be 45-degree. So always the maximum shear planes and this principal shear stress plane makes a 45-degree between each other. So it's directly clear from the Mohr circle without going into all the derivations and everything. So that's why Mohr circle is such a beautiful concept. You can just by looking at this Mohr circle and using some geometrical and trigonometric relation, you can come up with any of the equations that we had derived using some mathematical formulations. Okay. So next thing is that let's revise the properties of the Mohr circle that we had discussed in our previous slide. So first thing is that the center of the Mohr circle is sigma x plus sigma y by 2. The radius of the Mohr circle is square root of sigma x minus sigma y squared plus tau squared xy. And the third thing is your sign convention. So sign convention, when the face creates an anti-clockwise moment, it lies in the negative part of this vertical. Similarly, clockwise, positive part of the vertical. And also, like in many books, you may find different sign conventions, but for this video and just to explain, once you get familiar, it's all about then it's all about the sign conventions. You can use any sign conventions on your side, it's not an issue. Okay, so I'm going to write down those formulas for you. Okay, one more thing that I maybe forgot to highlight. Like if we look at this Mohr circle, we can also define these values of R and C in terms of the principal stresses. Like for this case, if you look, this will be your sigma 2, and this distance is simply sigma 1 minus sigma 2. Now if we are going to add it to find the center of this Mohr circle, that will be sigma 1, sigma 2 plus sigma 1 minus sigma 2 divided by 2, and it will give sigma 1 plus sigma 2 by 2. Similarly, if you want to find the radius, so the radius is simply equal to sigma 1 minus sigma 2 by 2. So that's what I wanted to highlight, that in terms of this principal stresses, we can also write the center and radius of this Mohr circle. Now, just to get familiar with the Mohr circle in a much deeper way, let's take few different cases. So you can try solving these things on your side with me so that you will get familiar with these things. So the first thing is that, like, suppose if I'm going to take a uniaxial case. So for uniaxial cases, how the plane stress is going, how the Mohr circle is going to look. So for Mohr circle, first thing is that if we look at this face, it's going to give us some sigma value and tau is 0. So it means that this point is going to lie somewhere on this horizontal axis. Now for this face, if you are going to look, this sigma is equal to 0 and tau is equal to 0. It means that it's going to lie on the origin. Now if we are going to connect these two points and take the midpoint of this line that's getting generated after connecting those 2 points, we are going to get the center of the Mohr circle, and the circle is going to look something like this. So for this case, the circle will pass through the origin, and the circle will pass through the origin, and it completely lies in the first and fourth quadrant. So just keep these things in mind, because if you are appearing for any competitive examinations like GATE, ISRO, PSUs, any examination, so these things will definitely help you. Next thing is that if you are going to simply reverse the direction, what's going to happen? So if you are going to reverse the direction, simply this Mohr circle is going to shift to your second and third quadrant. Next case is that if we take a case of biaxial case, in which your sigma x is equal to sigma y. So if we look at this face, this represents a point on the horizontal axis because it's a tensile in nature. Similarly, this sigma y also represents a same point on the horizontal axis. So what's the physical significance? Like, because this is a special case, it doesn't represent a Mohr circle. You can call it a circle, but it's simply a point on the horizontal axis. So the physical significance of this is that, like, if there is any stress system like this is present in your system, and if you are going to cut at any plane, the shear stress will be on that plane will be 0. Means all the planes, theta is equal to 0, 90, 45, 60, every plane is itself a principal plane. So this is a special case. Next, if we are going to reverse the directions, simply this point is going to shift in this negative negative horizontal axis. Okay, now let's discuss another case in which your sigma y is greater than sigma x. So if sigma y is greater than sigma x and shear stress is 0 on this element, this circle is going to shift away from the origin in this first and the fourth quadrant. Okay, next case is a pure shear case. So for pure shear case, if you look at this face, so this is something important. So if you look at this face, what you get? You will get a point corresponding to minus tau, and sigma will be 0. So 0 comma minus tau. So this point will be somewhere here. Similarly, for the orthogonal face, you will get 0 comma tau. So that point will be here. Now if we connect this point and find the midpoint of this line, you will get the origin of this. So this circle is again passing through origin, means the center of this Mohr circle will be the origin, and the radius of this Mohr circle will be equal to tau only. Now for this case, you can see for a pure shear case, the principal stresses values are also equal to tau. Now let's take another special case. Like if this, for this case, only the magnitudes are equal, but the directions can be reversed. So first thing is that on this face the tensile forces are acting, and on this face compressive forces are acting. Now for this case, it again represents the same Mohr circle. So what's the unique thing about this case? So the unique thing about this is that for all the case that we had discussed, that for all the shear stresses, like for this case, the point at which shear stress is maximum, there was some normal stress present in the system. Now for this case, if you look, this is a principal plane and this will be your maximum shear plane. So at maximum shear plane, your normal stress is 0 for this case. What it means is that this represents a pure stress configuration. So it means that if I am going to rotate this thing by 45 degree, it means if I am going to, this is a 45, if I am going to cut it like this, the stress that is going to be generated at this surface will not carry any normal stress. This only shear stress are going to be present at that surface. Okay, so these are the different cases that I wanted to discuss with you. Now what we had discussed mainly about the Mohr circle is that Mohr circle deals about the transformation from one set to another set, and it's simply a graphical representation of those transformation equations. So it doesn't mean it is only, so this means that it is not only applicable to the stresses or strain. It can be applied to any other applications in which the transformation from one set to another set is happening. So let's take few other application areas. Let's talk about few other application areas. We will talk about these things in detail in our upcoming videos. So for now, let's see. First thing is that we can compute the area moment of inertia at any theta. Means if we are going to rotate, like if we have some L section like this. Okay. So sorry for bad drawing. Now if I am going to rotate this L section in this configuration, now what will be my Ixx dash? So we can also compute these things using the Mohr circle. So we will look into these things in our upcoming videos. Similarly, we can compute the mass moment of inertia. We can compute the strain transformation and also 3D stress transformations and the strain transform. So these things we are going to briefly discuss in our upcoming video. So that's all for this video. If you like the video, please subscribe and like to motivate us, and don't forget to share it with your friends. You can share it on Facebook, you can share it on WhatsApp or any other sharing platform. You are free to do that. And in case if you don't like the video, please tell us where we can correct it so that we will amend those things in our upcoming videos. That's all for today. Thank you. Let's meet in the next video. Thank you.